So today we are going to be talking about solutions to non-homogeneous systems of equations. Does anybody remember what non-homogeneous means?
Doesn't equal zero.
Yeah, doesn't equal zero. So we're going to be talking about how to tackle those problems, and we are going to use our homogeneous solutions to get our non-homogeneous ones. But before we do that, we are going to do a quick proof. So in the book, this is theorem 3.5.1, and it states if you are given that capital Y1 and capital Y2 are any solutions to Y double prime plus P of T, Y prime plus Q of T, Y equal to G of T, and lowercase y1 and lowercase y2 are solutions of that associated homogeneous equation. So y double prime plus p of t y prime plus q of t y equal to 0. Then y minus y2 is going to equal c1 y1 plus c2 y2 for the lowercase one. All right, so let's go ahead and prove this. So for my proof, the first thing I want to show is that y1 minus y2 is a solution to our homogeneous equation. How are we going to show this as a solution? Yeah, we're going to plug it into our differential equation. So I'm going to have half y1 minus half y2 prime plus p of t. Sorry, that should have been a double prime. And then p of t half y1 minus y2 double single prime plus q of t y1 minus y2. And then I just noticed that right here I forgot a y there. So let's throw that in there. Okay. When I'm taking the derivative of things that are subtracting, how do I do that? Or what is it equivalent to? Each part. Yeah, each part. So I can basically take these derivatives and then just do some rearranging. And I'm going to get y1 double prime plus p of t y1 prime plus q of t y1 minus y2 double prime plus p of t y2 prime plus q of t y2 equals, well, we don't know what that equals yet. Since y1 is a solution to the non-homogeneous differential equation, what does this equal? G of t, perfect. So this is G of t minus, same thing here, y2 is a solution to the non-homogeneous, so it also has to equal G of t. And we get that this whole thing is 0. So we have shown that y1 minus y2 is a solution to the homogeneous one. But this, the c1y little y plus c2 little y2 is also a solution. And we haven't I can't remember if it's something you talked about with Dr. Thomas, but this encompasses all solutions to the homogeneous differential equation. So since it encompasses all solutions, cap y1 minus cap y2 has to be equal to c1 little y1 plus c2 little y2. So really bad proof and a really neat result. Why do we care about this result?
Like if we're given two solutions and we can figure out more solutions?
Yeah, if we're given two solutions, we can figure out more solutions. So why we care? We could then say that y1 is going to equal c1 little y1 plus c2 little y2 plus cap y2. So what this is going to do is it's going to give us a way for us to find the solution to the non-homogeneous. So the c1s with the little y1s, this is our complementary equation, and we call it y sub c because it's the solution to the associated homogeneous equation, so it's complementary. And then instead of using y2, we normally call it yp. So the solution to the non-homogeneous is going to be y equal to our complementary equation plus our yp, which is our particular solution. So what we're going to be talking about today is how do I come up with that particular solution? And it's going to depend on what G of t equals. Okay. Feeling okay with that proof?